What about just basic?
I finally got frustrated, and I talked to Richard or Raymond out of Yale, and I said, you know, the base sucks. He goes, yeah, everybody's been complaining about that. And I said, well, I redesigned it. And he goes, can you send me the files? I said, yeah, I put it together in about an hour.
What I want to do is pretty long.
So you're going to use the Yale hand?
Well, yeah, hopefully.
Okay. I thought you were going with that other one.
No, we have a little one now.
Light screen.
Okay. Hello, everyone. My name is Shalom. I'm originally from India. I'm currently pursuing my master's degree here at San Diego State in computer science. And today I'm going to present my thesis topic, that is the person-following robot. So basically what we're trying to do is we're trying to build different generations of the person-following robot such that, you know, we keep upping the technology that is used to build it as such. So back in 2005, say, we started building the person-following robot with only computer vision aid. And then we moved on and integrated fuzzy logic into the system. So now we've come to the 5th generation of this topic, wherein we're using fuzzy logic, but we're also integrating it with the accelerometer and the gyroscope data of a mobile. So the basic gist of this topic is basically the fuzzy logic definitions and the fuzzy logic sets that are used to build the classes which encapsulate the project. So this is what we're going to look at today. We're going to talk more about the fuzzy logic inference, like I'm hinted at, and we talk less about the robot system and the computer vision, since that's the module which we're trying to integrate within our system. So we're trying to make the hero of the project the fuzzy logic, and we're trying to use the computer vision as minimal as possible, because computer vision is something that's already established in the person-following field. Something such as fuzzy logic is still to be explored into as such. So that's what we're trying to get in this project. Starting off, we'll try and understand as to what exactly is the problem definition. So the person has a mobile phone, a mobile device with him. The application would have a start button, which one would press, and then the robot, based on the signals that are sent from the mobile, would track the person, and with the use of the computer vision, would get a sensing of the direction. Now, the robot that we plan on using is exactly the robot you see in the screen, which is a Segway RMP. It's a customized module that was built for San Diego State University. It's pretty old, so probably the processor and, you know, the other specifications that you'd see in today's world would be pretty better off than what you see here. But this is what we're trying to establish, and what we're trying to build is a robust solution. So if it works on this guy, then it pretty much should work on any other system. Here we'll have a look at, say, the previous versions that were built. And these are the versions that were built only based on the computer vision application. And this is how it used to work. So it has a servo motor in front, which controls the camera. And the camera works on a fuzzy logic PID module. So the camera has a continuous pan and tilt, which is controlled according to fuzzy logic. We'll get to the gist of the fuzzy logic that's used within the system. But I just thought that if you could have an idea of, you know, how exactly this project is shaping out to be, it will probably give you a better perspective into our project itself. So this is the computer vision module. And as you see that it's doing pretty much of a good job, but then there are cases of failure still that are possible within the system. Supposing if the person is not at all within the frame, or, you know, other cases wherein the person is lost entirely from the frame, that's the time the robot actually misses. And if you go ahead in this video, you would see a case wherein it actually fails because the person has left the frame, and then the robot doesn't know what to do. So at such cases, we're trying to avoid such cases by integrating the mobile device and the gyroscope and the accelerometer data. The camera, as I said, is working on a fuzzy logic BID. And yeah, like I said, that's the case where it just tends to say, I'm not going to do that much. So yeah. This basic generation was based, like you see, it was based on a monocolor scheme. If anyone could notice, the person's shirt that they're wearing is monotone. So it's only one color that it's being detecting. And it's not exactly doing like a person following. So what we're trying to integrate within our project this time is more or less of a person following robot, which actually takes the person into account, which sort of uses technology such as optical flow calculation and so on, which basically calculates the vectors that are generated from a person's body. So that would give us a more robust solution than the one which is present. So I'm going to move ahead to the next slide. So studying the architecture of the current existing project, we're concentrating more on the mobile device and the Segway RMP that we're using. So these are the processes that are happening on your mobile device. So there is a training phase, a profile match. That's only because each person can have different walks. I mean, a person's walk might vary according to his height. A person's walk might also vary depending upon factors such as weight or even gait, for that matter of fact. So there are many factors that affect a person's walk. So there is a training phase or a profile match for each person, and each person has its data stored within the database of the mobile once the person has completed his training phase. Once the training phase is done, the application then sends out the accelerometer data. This accelerometer data is sent out from your normal Android devices. That is, the accelerometer of the Android device is used, and that data is pulled out. The data is then worked upon by a Kalman filter, and the data is again shot out at the second time, but this time it is a filtered accelerometer data that we're getting out. Now, this two-stage communication, like I said, so the first time we're accepting accelerometer data, and the second time we're accepting filtered accelerometer data. Now there is a reason behind doing this, and if I blow up the RMP processor side, you see here that the accelerometer data is basically used for the magnitude calculation. Like for the magnitude of a person's walk, we want to know the exact reading, and hence not tampering it would make sense. However, when we need the number of steps for a person, and if we study the signal as shown later, we know as to why we need Kalman filtering and why exactly Kalman filtering is used within the application. So the magnitude calculation and the step count calculation are the two basic processes that are undertaken within the processor. And these two processes are worked upon by fuzzy logic modules, and this fuzzy logic module is aided by the computer vision, like you said earlier. Oh yes.
So I just want to make sure I'm understanding this.
Yeah.
The human being is carrying the mobile device.
Correct.
What you're hoping to get from the mobile device is how far the human being has moved.
Correct.
And you're doing that by the accelerometer data as the person takes a step. You're sensing those steps that are being taken.
Yeah.
And then you're feeding that to the Segway so that it knows to look for movement of a certain magnitude.
Yeah, it's searching basically for the distance calculation, what it's doing.
Thank you.
So that's what will happen within the fuzzy logic inference. So we get a distance within the fuzzy logic inference, so that the robot is always at a prior distance to the person itself, and we're using computer vision aid along with it, and that leads to basically controlling the motors on the Segway itself.
What's the magnitude? Magnitude of what?
This is the magnitude of your acceleration signal that you're getting from the accelerometer itself. So the hard signal value that you're getting from the acceleration itself, the magnitude of that is calculated. we'd be looking more into these details. I just thought I'd show you like a block diagram of the entire structure. You probably understand these processes more as we go into the slides. You had a question?
I was just going to say the magnitude, meaning like how far you step.
No, that depends on the acceleration. So supposing if I'm walking, the acceleration by which I'm moving, that is the acceleration that's measured. So there's an exact. See, if I take a step faster, then I'm accelerating and decelerating faster. So we study those signals ahead, and that really took a major chunk of time, because working on those graphs, we needed to make sure that they're perfect, and the Kalman filtering was perfect as well. So making sure that data was exact was basically top priority.
So just calling it the raw data is more accurate.
Yeah, raw data
raw
for the
data is all
magnitude
it is.
calculation. Yeah.
So can you memorize people
Um,
and detect which person's doing the walking?
yeah, that's stored within the database of the mobile itself.
So it can actually recognize people by their walk?
Yeah, once a person has already walked, he's pretty much going to have the same sort of ratios that are maintained, and you could pretty much find a match between that and the other ones.
If you're Monty Python, then you can tell the difference.
Yeah, as long as your acceleration graph stays the same,
Right.
you're pretty much going to have the same value. So yeah, that would work too. So this is the Android application. Like you mentioned, it does have a profile management, so it will recognize you if you come back to it. There is the training phase for new users. We plan on integrating all three axes of acceleration, because, like there'll be X, Y, and Z, and all three are important. We're primarily concentrating. We're still in the beginning phase of the project, so we're primarily concentrating on the Z axis, because the Z axis, like shown here, is the one that is perpendicular to your body. So now, supposing we're assuming that the testing that we're doing is we're putting the mobile, say, strapped here. So that's where usually people have their mobile pouches. So we're putting it in a pretty precise location, and we're using it on the Z-axis. So we're calculating one axis data first, and then we plan on incorporating the other two axes within it. Later on, supposing if you have your mobile phone here, you pretty much have a generic axis, so as to say. But primarily for convenience sake and to study the acceleration data accurately, we're using the Z-axis, which is perpendicular to the mobile. So this is the acceleration graph, or so as to say the raw data graph that's put up. And like you notice, there's a lot of noise, so as to say. Noise wouldn't be the exact word, because we are getting the true value out, but there's no definite shape, so as to say. And what we're trying to do is we're trying to find out the peak magnitude from each case for our magnitude calculation. And it really hurts when you get this sort of data where you get a double peak, which isn't exactly a peak. So supposing if you blow up the video where you're walking, you've noticed that if I'm taking a step during this same time, these two double peaks, for some reason, are found at the same time. So this doesn't really help our cause, so as to say, because we're just taking one step. So we're accelerating and decelerating only once. So originally there should be one peak and one peak down. So this data here, for whatever reason, has to be removed or smoothed out, for example. So there are a lot of techniques, especially from the field of signal processing, that we can use.
So is that like my fat bouncing up and down as I take a step? Or?
It's pretty much random, because we tried moving slow. The only thing that does show up is the slower you walk, the less it reduces. So I'm guessing it's a jerk in the step that's being caused, because the more you increase the speed, the more bad signals you get. So I guess it's the jerk to do, because when you're trying to walk faster, it's basically the jerk that's causing it. Yeah. So that's what's happening there.
Each one of these is a step. every one of these peaks we're seeing is a
Yeah,
step.
these peaks are generally the steps of a person. So what we try to do is we try to walk uniformly, like you do in any process. Like in the beginning, you keep it as simple as possible so that you get maximum data out. So what we've tried to do is we like I said, we fix the axis so that the z-axis is exactly perpendicular, and at the same time, we're also trying to keep our walk uniform, so as to say. So if we're walking fast throughout the run, so that we know that all these peaks belong to a fast walk. And then the next time we've done it for normal walk and slow walk as well, because the only way to entirely understand a system is to get down to the basic level. So these are the acceleration data for a fast walk. Now this is for a normal walk. Like you noticed earlier, I didn't point it out, but the initial magnitude was at 4. Yeah, and this is now fallen to 2. So that's a trend that we see, and hence we use the magnitude calculation because it is important data to us. So it's come down from 4 to 2, and we still see those peaks, those double peaks, which are disturbing. But the magnitude that we're getting from it is the original and is of use to us. And this is for a slow walk. Now, like I mentioned, in the slow walk, you can see that there are a few peaks which are perfect, which are brilliant. But we still get those double peaks. So I'm guessing it's because of a jerk in the step of a person's walk or something to do with it. So, and you see that the magnitude has fallen to 1.5 here. So it's pretty much of a ratio of, say, 1 is to 1.5 is to 3. You can see something like that. This is just to give you an idea of the comparison of the fast, normal, and slow walks. This is taken on an average heighted person. It depends on how you define average height, but these are basically my values of walk. So, and this is fast, normal, and slow equally. So this is just to give you an idea of how the graph is changing. Now comes the interesting part as to how we manage to actually solve the peaks, because you can actually do it by many sort of equations. The Kalman filtering, like known, is basically used for noisy systems. So we get noisy data in, and we're giving out data that's less noisy. You can never totally eradicate the noise from the system. I mean, it's not feasible to completely eradicate the noise, but we've tried nonetheless to get the noise out, and we've been pretty successful at it. The alternatives that were considered to Kalman filtering were the weighted average filter, which is the Segway filter. But the problem is with this filter or with any other filter is that it has a mathematical equation that is pretty much the equation of a line. And it would work in a case if a person had uniform motion. But we're building an application that is real time. So a person may not have uniform motion at all times. So that's where the Segway filter or any other filter that conforms to a mathematical equation as such of a line specifically would fail. The important things to consider within the Kalman filter and that drastically affect the dynamics of the filter, so as to say, the Q and the R, which is, this should be R, not H, I'm sorry. So the Q and the R factors, which are the measurement noise and the covariance of the process noise. These two noise models are basically the noise that you're getting from the system itself and from the entire process of the Kalman filtering. So these are just like these are the equations that are used within the Kalman filter. It has a predict and an update stage, which sort of self-corrects itself continuously.
How many states is your Kalman filter?
The number of states.
And what are they? The X dot, Y dot, Z dot, the accelerations?
No, we're just working on one as of now.
Oh, really?
Yeah.
Okay.
So it's
Just the Z?
just the Z as of now.
Okay.
So this is your original acceleration signal that is blown out, and these are the Kalman filter values that we got from them. And like you see, the Kalman filter has done a pretty good job at maintaining the ratio of the signals, and at the same time, it's removed the double peaks from all of the values. So this makes it easier now for peak detection, because that's what we're basically interested in, to calculate the exact number of steps that the human has walked. So here you see there's a peak here, there's a peak here, and at each level it has sort of pulled it out. Now the value of the Q and R depends on how much is going to pull it towards the zero and how much is going to pull it away from it. So we need basically like a good mix of the two, and that's the only thing that changes within the Kalman filtering. The peaks can now be easily identified, and the peak detection is pretty much done by a peak detection algorithm, which is separate from the Kalman process. And we're using a sort of hard cutoff for it because we haven't got there's a lot of math that goes behind the model otherwise, because you have to pretty much work backward from a Riccati equation, which we didn't think as of this point is feasible enough for a real-time solution. So we're using sort of a hard value limit cutoff for the peak detection, which is the next step of our process. So how does this peak detection work? So the peak detection is basically working on a delta calculation between the signal points at between two consecutive signal points, and then it further takes the delta of that delta. So it's an elimination process that's keeping on eliminating the deltas, and the ones that are the highest tend to come out as the peaks. So after Kalman filtering is applied, this peak detection algorithm works, and we pretty much get a good result, as in every peak that is determined from the Kalman filtered signal is pretty much shown up after the peak detection. So like you see here, if there were two signals, they'd be disregarded because the delta of that one is higher. So at a delta count that is sufficiently high, that's where your peak lies, basically. So that's the principle that we've been working on for the peak detection. Now comes the main gist of the project, and this is where your computer vision application and also the acceleration data, as in the distance measurement for the Segway, is based on. That is fuzzy logic. Now, as an introduction to fuzzy logic is pretty much different from Boolean logic, or pretty much from whatever logic we sort of undertake within our C, C++, and Java normal languages, because we're using constructs, but we're pretty much hard defining values, even to a certain extent. The fuzzy logic model allows us to introduce vagueness or randomness, so as to say, within the system. This randomness is important because to make a system more or less human-like, you pretty much have to allow the system to think within all the spheres of the sample set. So a machine would pretty much think in terms of 0 or 1, but a human would be able to decipher this color from that color and that color, which is towards the end. And that's what basically fuzzy logic enables a machine to do. So the basic logic of fuzzy, that is a basic principle behind fuzzy logic, is where we keep on categorizing each of these data values into sets. And set theory is basically what we have in mathematics. So it's not a new principle, so as to say, but it differs from the set theory in terms of set theory is basically crisp. So if you had to classify, say, segregation of men into short, medium, and tall people, you pretty much have this short, average, and tall. But a person at 179 meters, I'm not sure of the units. I'm sorry. Yeah,
Centimeters.
Yeah. So that would pretty much, be unfair to him because he'd be in the average class when he's just say 1 centimeter away from being tall. So that's what fuzzy logic doesn't do to a person, because a person can be average to a certain extent and can also be tall to a certain extent within that case. We study the entire process in detail, but this is basically just the outer gist of it. So fuzzy logic given to the machine is considered to be, if you were to code it to a person who doesn't know any language, any coding language, it would be represented in the form of, say, 2000 if-then statements. So each line would be if this, then that. Like each, as humans, we take decisions based on the same principles. So if supposing if it is hot, then I will wear my cap today. And then the second decision is if it is extra hot, then I'd be going in the car. So each decision is based on an if condition, and where X is the antecedent and X is the precedent and Y is the antecedent. So that's how fuzzy logic works. There are two approaches, which is the Mamdani fuzzy inference and the Sugeno. The Mamdani is computationally more expensive, but it does offer great accuracy and is more widely used. Whereas the Sugeno is used for real-time systems, but gives you only with a less trade-off. There's a very low trade-off between the two, but it does give you slightly less accuracy. The Sugeno principle. The basic steps in fuzzy logic are your fuzzification of the input variables, wherein we're actually putting the values to their sets, we're conforming them to the sets that they belong. The rule evaluation, like I said earlier, humans tend to work on the basis of rules. So what rules fire and how exactly the system processes to it. The aggregation of the rules. So supposing if it is very hot and at the same time, I have to reach early, then what do I do? So that aggregation of rules is mentioned in this sector. And lastly is defuzzification, because finally the machine is not a human. We need to convert it back into a number to make it understand. So what we're doing here is we're actually getting it to our level and then sending it back to the machine level. So just to explain fuzzification more, just to clear things out, fuzzification, like I said, is set theory, but it's not crisp sets. A person can belong to either one of the two, and hence you see the intersections. So in the example that I gave earlier of short, average, and tall men, a person can be short and tall if he is in this intersection, if anyone guessed. So these intersections allow the fuzziness, and the degree of these intersections depend on how fuzzy your model is defined as. So let's take this value, which would probably be, say, around 40% of the entire. The entire x-axis is known as your universe of discourse, which is your sample set, basically. And this is the membership. The membership is allowed to be only from 0 to 1. So before using any fuzzy logic model, we make sure that we normalize the data beforehand. So this is the membership value, which is belonging for the short set. Short set represented by the red marked region. And at the same time, we also get the green marked region, which is your average height. So this is how the person can have a membership value with short as well as average height at the same time. Now, how do we use this membership value? And this is where you have a rule evaluation as such, where you know that a person is, say, short, okay? Or take for the example wherein I gave earlier, wherein it's hot outside and I need to reach at the same time. So what is the urgency with which I need to reach my destination, and how hot is it? So I consider both those two rules, and then it depends based on a database storage of our rules, which are basically those 2000 if-then statements that we have, as to what rule fires, and that again is a fuzzy set. So your answer, the output that you're getting, so supposing is that it's hot outside, and at the same time I need to reach fast. So hence I use the car and I won't use a bicycle. So the use of a car and how urgent the use of a car is represented by that set C2. So that's how it works. So you have if condition 1, condition 2, and output. So that's how it's shaped. And we use operators, our logical operators such as or and. So supposing if in our case it is hot outside and I need to reach urgently. So in our case we pretty much go for the and operation. But you can also use or you can use any of the other logical operators which you can use within fuzzy logic. So this is the rule matrix as such based on which the fuzzy logic is shaped. And like you can see, there is a sort of trend to this rule matrix. Like all the elements are diagonally shaped. So moderate, moderate, moderate goes diagonally shaped. And this is a characteristic of the rule matrix within fuzzy logic of any system that is built. So it's sort of randomized, but then it's generally randomized, which allows us to put an algorithm to it. So that's how it helps us, fuzzy logic. And this is the rule matrix which we established for the previous example, wherein we have 3 sets. The choice of the variables within the rule matrix is purely based on the constructor of the fuzzy logic model. So a person can choose to anywhere within 3, 5, 7 variables. You'll only be increasing the fuzziness because there'll be more interceptions within the module. But it's pretty much based on how fuzzy or how accurate you want the system to be. This is the aggregation of rules, and this is primarily where the Mamdani style changes from the Sugeno style, wherein the Mamdani principle uses, supposing you're getting the AND value of all the operations, it's going to take the entire region, and the entire region is going to get, you're going to calculate the center of gravity of that region to convert it back into the machine level language. So you get this area and that area and that area. Then you're performing your ANDing operation. So you get that cutoff, which is basically the output. And after the aggregation, you basically calculate the COG of that region, which would tend to be somewhere here. And that would be your output variable for the machine to follow. And that's how simple it is, because you're not doing a lot of hard calculations, or you're not including Poisson's ratio to intercept something. But these are probabilities that are included within the system, but they're only using set theory. So that's how simple it is, and at the same time, you're managing to control the robot. In contrast, the Sugeno style, it allows you to only get the mid value of each set. So that is a limitation, but then at the same time, you're also getting the benefit of not having to calculate the center of gravity, which at times might be a computationally expensive operation. So that's the only difference between the Sugeno and the Mamdani. So in this, you pretty much be losing on accuracy, especially if your sets are big. But the Sugeno style is more likened for real-time systems because it sort of gives you a faster calculation. Defuzzification, like I said, is the process of calculating back the hard value, as in the binary value or the integer value from your original. This is a representation of the mu A is a representation of the membership of each variable, and that's how you calculate the COG impact. So how did we use fuzzy set theory basically in our project? I'm sure many of you must have pretty much got an idea of it by now, but we basically told the person we have two phases within our project. One which is the training phase, and the other one which is the runtime phase. Now, within the training phase, we told the person to walk for a certain amount of time. He starts the application and then lets it run, and it basically sends out a buzzer. So what we do with this data is, because we do not want false data, and you're never going to get data from the starting points. Yeah, like if you remember the graph, the start was initially pretty jagged, and then it sort of stabilized the walk. So hence we perform an alpha trimming operation, which basically cuts out the initial and the last part of it, and we then work on that. This data, which is then worked upon the fuzzy sets. The fuzzy sets sort of compromise it and get it working accordingly to the slow, normal, and fast. So there's a cutoff for each, which is slow, normal, and then fast, and that's how it works. So here you have the person walking. Person is instructed to move normal walk within the training phase. We try to avoid the training phase, but then the differences in a person's walk varied so much from one person to another that it's virtually impossible, unless you have like a superseding fuzzy set even over it. It would be not such a great idea to use it on everyone, just conforming it to a single person, because my walk would definitely change compared to another person's walk, especially if there's a difference in height and step size. So that's where everything changes, and especially when you're setting the thresholds for the fuzzy sets, since it's dependent on the walk style, that's where things change. So we build our fuzzy sets like shown earlier, according to slow, normal, and fast, so that it has a membership value with each of the sets. And then you come to real-time person following. Now, within the real-time person following, we're taking the accelerometer data, the bursts of accelerometer data, and the filtered accelerometer data at equal intervals of time, and we're fixing that to say 10 seconds or so, because we need the robot to calculate the fuzzy sets and to establish a good reckoning of the distance between itself and the human itself. It needs to get a good approximation of what the signals are exactly. So there's a 10-second period that's taken into account, and the fuzzy sets are working accordingly. And after each 10 seconds, the robot gets a defuzzified value, which it's instructed to move along. So that's how the system works based on the fuzzy logic. Coming over to the Segway robot system, this is your Segway. It's a pretty old structure, but we're supposed to make do with it because this is the only thing we have in our lab. We're thinking of customizing it because it's got a pretty old processor, which is the LabCam processor, which works on it, and there are external circuitry that are connected for the servo motor on top. The servo motor on top works with PID control as well, which again fuzzy is included within to control its system. So this is basically the architecture that we'll be working upon for the Segway robot. And the computer vision module that was established, like I said earlier, was basically a region growing algorithm that was used. So like you notice again, there is monotone color within the figure. So basically a region was established, and you had pixels growing out. So more or less like a flood fill, similar to a flood fill algorithm. And there was a match criteria based on that flood fill algorithm as well. So that's what the initial research was done in. But we're trying to eliminate this computer vision model by integrating into it optical flow calculations and other ahead modules. But that's all to do in the future work, because currently we're still working on the fuzzy logic model. So that's where we're at. So to conclude we're basically using, like I said, the fuzzy logic model just to make our system more human-like, and also to provide a different solution, because you have computer vision already established in today's world. What we haven't probably investigated fully into is the fuzzy logic side of it, and also as to how we can use mobile data as such. So that's what we're trying to do within our module and my thesis project. Thank you. Does anyone have any questions? Yeah.
I'm wondering if the performance benefit and the cost between the two fuzzy logic approaches is inherent to the differences in the approaches, or is it based on the algorithms that you apply with each approach?
As if you're saying the differences between the approaches within fuzzy logic, right? The Mamdani and the Sugano.
That's right. Is there a hard, fast difference in performance and cost, or is it dependent upon the algorithms you apply when you're using each?
No, it's pretty much on the algorithms you're applying. So it's only because the Mamdani has the COG. Like if you want a really probably for a security system, and you're not so much looking into how fast it does it, but how efficiently it does it, then probably you'll use the Mamdani principle, because you want to make sure that the person you're looking at is the person you're looking at in a security system. So there you preferably prefer Mamdani, but if you want your system to execute faster, then you go for Sugano. So it's pretty much on the algorithm rather than the system. Yeah.
You mentioned how there's like a training phase for each person.
Yeah.
What's involved with that? Do they have to walk at different speeds?
No. What we've envisaged our training phase to be is the person walks for a certain distance, and once we get enough counts like on the application, so say about 10 to 12, and we got them within the stabilized region where we've not got false values initially and the deceleration towards the end. That's where we take a reading, and the application buzzes by itself. So a person is instructed to walk his normal gait, which is what a person can perform pretty much. And what we're guessing or assuming as of now is that like there was a ratio between the magnitude of the fast, normal, and slow walk for my experimental run, that be pretty much a ratio, an established ratio. We've done it for say 4 or 5 people, and we're pretty much getting a ratio which is established between the fast, normal, and slow walk. So that ratio would be adjusted based on this training phase for each person, and his fuzzy logic sets would be built. So a person doesn't need to walk different speeds as such, but he just needs to walk his normal gait for 10 seconds.
Is that ratio consistent among different people?
It's pretty much, but we still need to test it, because you can never say, 4 or 5 people can still have the same ratio, but it's sort of consistent. Yeah. Yeah.
So I'm kind of curious about you're getting the number of steps that the person has taken within 10 seconds.
Correct.
And maybe the magnitude of the steps or the speed at which they're walking. So you have some idea of the distance that they've covered, right?
Correct.
But you don't know what angle they walked at.
Correct.
Right? So how do you compensate for that? I mean, if the person walks to the left, I could see that the computer vision system will figure that out. How do you deal with people walking at like 45 degrees or walking towards or away?
Yeah.
Well, hopefully they turn around first.
Well, but the computer vision system isn't detecting that at all, so it doesn't know.
Yeah, we don't need to basically rely entirely on the computer vision system as well, because then there's no point, because where if the person walks out of the frame, it's pretty much going to fail even in this case. So like you saw, there were 3 axes for the mobile data. So the mobile has its z-axis, x and y. So what we're operating on is your x and y data as well. And we're going to build fuzzy logic, and then there'll be Kalman filtering over those values as well. So that's when we incorporate it into the system, and it will basically be doing fuzzy logic calculations.
So you're going to sense when the person has turned.
Yeah, so a turn would probably be a delta in x on the x-axis. So that's what we're fishing for.
Yeah, that makes sense. So the other thing I was kind of curious about. Oh, I'm sorry. Go ahead.
No, please.
Was the amount of time. 10 seconds seems like an awfully long time. Was there a reason why you didn't go with a shorter? I mean, in other words, what I'm understanding, and maybe I'm misunderstanding, is that the robot basically isn't going to react for 10 seconds.
Yeah, sort of.
Okay.
Yeah. So that's the experimental run up that we're getting now. But probably with change, especially in the application frequency.
Then you'll
Yeah.
narrow that
So
down. Okay.
But since we started working with this application frequency, and if we change our application frequency now, it's pretty much going to shatter off everything.
Yeah.
So yeah. So currently we're sticking to the 10-second, but yeah, we definitely. But that's pretty much dependent on the application frequency. So that wouldn't make a difference. Yeah.
Who was first?
So, since you have three-dimensional accelerometer data, are you perhaps doing some sort of pathfinding, or are you still shooting for a direct line to where you assume the object is, the person is?
Yeah. We'd have. You can think of it as a path which has a number of waypoints, and the robot is basically traversing from one consecutive waypoint to the next consecutive waypoint within that path. So if a person has walked, say, like this and then like that, the robot will pretty much try to mimic it, so as to say, because it's going according to the waypoints. Or it will if it's within the time barrier, it will take an average of those two and then go straight to it. So it will pretty much follow waypoints, and yeah, it's more or less a path that it's moving.
Yeah, you could see that in the film that you first showed.
Yeah.
That he's walking and then he'd move over this way. That robot would go this way. But
Yeah,
there was a
with it.
couple times when he went this, and it just went
Yeah,
and followed it. That was interesting.
Yeah, so that is a fuzzy within the computer vision, but the fuzzy within the accelerometer would even be more trustworthy,
Right.
because then you're only using the computer vision as an aid. And the path where it just forgets him and goes out, that pretty much wouldn't happen.
So you're not doing any data fusion on the accelerometer data and the computer vision data?
No.
No.
We're trying to keep the systems apart, so as to say, and we're trying to keep the computer vision as minimal as possible as of now.
I'm back to the 10 seconds. So if the person starts walking,
Yeah.
10 seconds later the robot moves, then stops for 10 seconds.
So this is just development.
Yeah, that's what's happening now. But we're working at an application frequency data that is pretty much dependent on. If you change the acceleration, just go through that.
It's going to take a while for that to come back
Oh,
on.
I'm
You gotta
sorry.
turn
Yeah.
the projector
Okay.
on.
So
It'll get there.
So-
It just-
so-
oh, there, that was quick.
so basically, if you, if I can go. Yeah, so like you see, this is the number of samples that is taken. So the number of samples that it's taken would definitely depend on the application frequency. So this 10 seconds works for what you call game frequency of an application. The frequency at which a game works on an Android application. But if we manage, and we can increase the frequency. So if we do increase the frequency, the only things that would be needed to change are your variables within the Kalman filtering and the fuzzy logic set data as well, which would trouble us in our experimental runs as of now. But once it's out in the open, it would pretty much be of a lesser. I mean, that wouldn't be a constraint. So,
But I mean, the video you showed, the robot doesn't really stop. I mean, it seems to be moving all the time,
Yeah.
following the person.
That's only vision.
Right. But you're saying now with this fuzzy, it's going to move, stop for 10 seconds, then move.
yeah, but if we increase the application frequency, then that 10 seconds could even be brought down to point something seconds. So it would pretty much look like the computer vision, and it would be more useful because the cost that goes within the computer vision, I mean the number of libraries that you have to build within the processor and keep it. I mean, you could pretty much run this fuzzy logic model on a simple chip. You wouldn't need to use an established processor. So that's where everything changes. So in the end, this would definitely be a much more quicker solution. It's just the constraint of the application frequency, and for our experimental runs, because like I said, we need to make everything basic for an experimental setup so that we study it properly. Because if we were working at that higher frequency, we probably would have missed out on these peaks. So, just to smoothen out everything and keep it as simple as possible, we're working at a slower frequency, and then we upper it as we near.
You can't work, sorry.
No, go ahead.
Work like on a moving window, so you're.
Yeah. So that's what I'm sorry. I think I forgot to mention that we would be working on where first the interval is taken 0 to 10, and then 1 to 11, and then 2 to 12. So that's how the samples would be calculated. Yeah.
So it's more continuous, but it would still have a 10-second delay, and then you're going to narrow that down so that
Yeah,
you have maybe a 5-second delay.
Yeah, and in the end, with the application frequency, it's just that we're pretty much within the modeling of data and incorporating the values. But yeah, we've thought about all that, and even the windowing. I've forgotten to mention it within the slides, but yeah,
So the other thing I was curious about is I don't know how good accelerometers are in cell phones on average.
Yeah.
But if you just filtered it down to nothing, can you get a general sense that a person is moving in a particular direction? I mean, right now you're getting the step data, right? So this, jerking forward and back as they move.
Correct.
Can you also get like I'm moving forward at a more gradual pace and have a sense then of what direction they're going? Or have you just not tried?
What you get from the signals is basically an acceleration and a deceleration.
Right. No, I understand that. But what I'm saying is, if I move from that end of the room to that end of the room, not only have I accelerated and decelerated every time I take a
But you
step,
also moved forward.
but I've also done this huge long acceleration and deceleration. Can you make use of that, or is that just out of range?
No, that's a valid point to consider actually, because if you're taking like a check, like say between every few windows, you know whether a person is moved based on his accelerations along the 3 axes.
Right.
You get pretty much a relative distance or a point as to where he's moved. So yeah, that would be possible. Yeah.
So to retrieve the acceleration from your Android application, you're just I looked at accessing acceleration values from this. So you're just grabbing like the low level raw acceleration.
Yeah, that's it.
Okay. Yeah, I think there's a few other ways you can access it that's supposed to filter out some of the gravitational effects that may be helpful for these other things in the future.
Okay. Yeah.
And most cell phones have compass.
Yeah.
Have you considered using that, tying that in also?
We're thinking of including the gyroscope data as well. So, I mean, you want to know as to how much it's wobbling up and down. That would probably be information that we're losing out on. So, the gyroscope data is something that we're planning to integrate with it as well. Definitely. Yeah.
So then you're transmitting all of this data back over like Wi-Fi, or?
Yeah, and that is a problem because a Wi-Fi strength can decrease or increase at any point of time. But we're trying to establishing a separate band for it wouldn't make sense because then you're restricting its use. So we're trying to get it to work. We're trying to more or less look around, but then that takes us to a whole new dimension and probably be a whole new project.
So I actually mentioned that because thinking back to my old Navy days, there was a radio direction finder on the aircraft, and you could figure out where any radio source was by using that. I'm just wondering if you could put an RDF on a robot and home in on the cell phone's Wi-Fi signal.
Well, you could. You just need 4 antennas, and then do phase and parameter.
Now, how do you know which one is the robot though, or which one is the cell phone? You can't really ask it the MAC address.
You could. There are ways to build, say, a secure channel. Like you could even probably use like RF and then work at a frequency and log bit it the other way and work at a sort of customized frequency, so as to say. So
Reprogram the Wi-Fi chip on the cell phone, you mean?
yeah, exactly. So
Never mind that one.
FCC
Yeah,
might have
Yeah,
something to
so,
say
so
about
it does
that.
become usable.
Yeah.
But yeah, we need to look into that.
I wonder if there is a way though of tracking the
Well,
There is.
line of sight to a.
considered like the Bluetooth, pinging the Bluetooth, or
No.
putting some other, I mean, even the cell phone could give you its GPS.
Correct, yeah. We thought of the GPS, but then we're trying to make, since it is a thesis project, we're trying to make the system as stable as it is right now within its domain, and then looking into another domain, because we're only going to mess our work up if we look into two domains simultaneously. So yeah.
So it might be beyond the scope of what you're hoping to achieve with this thesis, but going back to the waypoints, have you thought about what some of the real world criteria or influences might be that would determine how much you direct toward line of sight or hard position that you've established versus following waypoints? For example, is there a situation in which it might make more sense just to go directly to where you know the person is rather than following their exact steps to get there?
Yeah, I mean, if you do break it down, you could break it down to following it. You could customize the system as to how you want it to do. Like, come again, like if you want like the robots to follow a security surveillance where you wanted to follow a guard, say, after a certain amount of time, like at a certain distance. Or you wanted to follow, say, for example, another robot where you have a completely automated solution. And you have one robot there and the other robot there, and you wanted to follow each other on an infinite path. So then you probably use the path algorithm, or then you could break it down and average it out, or use the other one. But this project is basically more towards a golf caddy sort of system, wherein the robot is used as a golf caddy. So the robot is used as a golf caddy, and he keeps following you. And it's pretty much the averaging that we'd use, not the path exactly. So the waypoints would be estimated to an average, so that it just comes to you straight away. And that's where the speed would matter, because you wouldn't want a robot to come darting at you when you just want to stick from it.
Yeah, but you don't want it to fall into a sand trap either.
Yes.
So that, if he walks around the sand trap, I want to follow him around the sand trap, not jump into the sand trap and come out.
Well, shouldn't follow you onto the green either.
Well,
Right?
then you've got to get your camera to do slam mapping and figure out where the hazards are. And at some point, why don't you just program the robot to play golf and say the hell with it?
There you go. Yeah, I like that one.
It could be your partner.
Iron
You could always
Byron.
make sure it loses.
Yeah, exactly.
Here's a trick question. What are you gonna do if someone puts on a pair of roller skates and their acceleration?
No, I don't think we'll be considering that. Yeah. Yeah, because you wouldn't even need to be on a roller skate. Probably if you start running,
Carrying something.
then this robot's not going to agree with you either. So
I expect running to have more acceleration. I'm not a bio. I don't know what the word is for it, but I wouldn't normally know about the acceleration that you have when you're running or walking. But I would expect walking to have less acceleration and then be tricky to figure out more than running. Or is that different than what you see?
it's actually just the opposite way, because the slower you walk, the more sort of uniform the readings are coming out. So it's as good as slowing down a system.
A lot of the
So,
differences
the slower you ask a system to work, the better it works.
So running is different.
Running is like hard jerks. So yeah, that's definitely going to be much more difficult for the Kalman filter.
Did you try running?
Yeah, we did try, and
in your pocket.
since the Kalman filter tends to push it towards zero and push it back up, or either one of the two, we see a constant deceleration that is superficial. It's not supposed to be there. So that's because the job of the Kalman is to do that, but that's where it's failing. And you'd need probably fuzzy on the Q and R, because the measurement noise and the process noise is changing them. So you need a fuzzy on that, and then it becomes out of scope as well.
So I'm curious if you've done any. I have to say I'm really impressed that you can even figure out where the strides are from the accelerometer data. That's kind of cool. Have you done any metrics on how accurate your measurements are for?
Yeah.
like a distance moved.
Yeah.
Yeah.
So we have like only say a 5% error rate between the actual distance covered and the distance that is coming out from our fuzzy logic models. We're still very much in the preliminary stage. I mean, we've only worked on 4 or 5 people, but 5% for starters, 4 or 5% is pretty good. So
That's
yeah.
very impressive.
Yeah.
Yeah.
And especially when we're getting at something out of set theory, it becomes even more, because we're not using heavy classes or anything. It's just one class and one code.
So are you thinking about other applications for this other than just the following robot? Because I'm thinking about things like being able to tell where a human being is within a space. So maybe it's not the robot that wants to know where the human is, but the building wants to know that he's about to walk through the door or whatever.
Yeah, there are many other applications of fuzzy logic where before this project, in my undergraduate project, I'd used fuzzy logic for an autonomous robot, which is pretty much without any sensors. So it doesn't have any navigational sensors, so as to say. So it doesn't have any sensors which detects walls or it just has a camera in front of it, and that's how it works. And it knows at all times as to where its position is. I mean, pretty much on a virtual grid. But at the same time, it sticks within that virtual grid and it's searching for stuff. So it builds a virtual grid around its surroundings, and it does that. So that incorporated fuzzy logic as well.
Sounds like SLAM.
No, I am not sure of what SLAM is.
Simultaneous location and mapping.
No, but I don't know the.
Okay. So one last question: have you ever heard of CMAX? CMAC. It was a guy by the name of James Aldous. Many years ago, came up with it. Sort of halfway between fuzzy logic and neural nets.
Oh, okay.
So you might be interested to read about that.
I am. Yeah.
He's a graduate student.
Yeah. He has no time to read.
So you're trying to keep all the processing local to the robot then?
Yes. Yes.
Not relying on internet connections.
No. Yeah.
Well, except
We
for
do have the
communication.
Wi-Fi. Yeah.
Oh, well.
So
The guy's got a cell phone in his pocket.
yeah. So that is out there. Yeah.
But
The
GPS
Wi-Fi
is only
there.
so accurate, right? It's not.
Not unless you use.
Well, actually, over the
Might be
space of
outdoors.
a golf course,
That's pretty accurate.
it could get fairly accurate, I
If
suppose.
you get under a tree.
That's where you get your big error correction signal from your overall.
A differential station.
Yeah.
Have you thought of adding any extra hardware just to get another source of data like an infrared distance?
No. No, we wouldn't want to do that because we're trying to make it as efficient as possible for this system. So that would just be like cheating, so as to say, within a project. So yeah.
Cheating.
Yeah.
So if it's outdoor, you'll be swamped by daylight.
And yeah, IR, yeah, the daylight would blow out the IR sensor.
But with this, it seems to me like if there's any kind of drift, then over time it's just going to keep getting worse, and eventually your robot loses your person. So
No, that's what happens in fuzzy logic, because if there is drift, the robot would align according to that drift, and it would work within that region. There's an important aspect that you touched upon there, is if you go to see, so if you go to see within this rule matrix, you have these rules which are set out, but if you notice these blank spaces at the top corner and the bottom corner. So what fuzzy logic does for you is it keeps your system within these states. So the system would never go out of the state at any point of time. So the least it could reach is meager and meager, and the max it could reach is lot and lot at the very high conditions. So fuzzy logic is modeled such that your system is kept within these states at all times, and it doesn't go out of it. So if it's drifting, it would always, and it's always going to try to bring a system back to the model. So it's as good as, working within that universe and trying to bring it back to the middle value. So it would never go out of bounds at any point of time.
okay, but by drift, I was thinking more that the
Robot,
the person's gait would change,
yeah. So
and then how could the robot respond to that? How would that?
that's what it does. See, because imagine it this way. Supposing if the person drifts outward plus left x, so the robot goes plus x out as well to try and align it back to moderate. So the next time the person goes straight, it has to go only straight. If the person makes another plus x, so it's aligning it back to the moderate that's in the center at all times. So if it's going plus, it brings it back to 0. Then if it goes plus again, it will again bring it back to 0. So it's as good as saying, I'm following you. So I take this turn, it goes back. So this is now 0 for the robot, because if it walks straight from here, it's going to be 0.
If we kept to the single direction axis system, then if the person moves slightly faster than what was expected by the game, then they could eventually outdistance the robot.
If the person starts running very, very fast.
Well, even
Only
as
if you
a
go faster than
small
the
thing,
robot
if
can go.
you're going over a long distance, then
Well,
the errors would
No, it's going to minimize error.
Error rate.
That's
right?
That's
So
what
it's going to stay right there
Over
with you.
time, like is what he's saying.
It-
So
it-
maybe
it
like a
accumulates.
feedback,
Yeah.
Like the camera.
Yeah, the camera can, probably we'd establish a feedback system for that as well. And that's what the camera is using, basically. It's making sure that this guy is doing his job. That's the only expectation we have from the computer vision aid. So, yeah.
But 5% is a lot. If you walk 100 yards, then it can be off by 5 yards at the end.
Yeah, but that again, we're still on. This that we've churned out is pretty much the first set that we got. So for a first experimental set, 5% is pretty much workable on, and it's just a matter of exacting those fuzzy, like as to where the fuzzy sets cut the universe of discourse. It's just a matter of determining those properly and the intersections. So that's pretty much workable on. It's the only thing is it's a trial and error process. So yeah, it's going to go down, but it'll go down gradually.
And again, you have to have some other sensor system that's providing an additional input, like the vision system, or
Correct.
Yeah,
something
so to
else.
check
or
whether it's correct. or not.
ultrasonic ping or something like that.
Yeah.
Have you thought about trying to do an ultrasonic ping from the cell phone speaker?
Oh, gee, thanks.
Wouldn't work in my pocket.
Sure, it will transmit through the cloth. Do you think?
Ultrasonics wouldn't go through that.
There's
What if you're talking on your phone while the system is going?
Yeah.
there's actually a guy. Oh, I'm sorry. Go ahead.
Well, on that matrix you had,
Yeah.
you explained that you could change the number of rows, but you didn't explain how you came up with the number of columns.
So laptop. No, I'm sorry, that'll take time because my laptop's gone off too. It's just that it depends on the condition. So coming back to the example where I said I have to reach a destination and it's hot, but at the same time I have to go urgently. So now the heat factor and the urgency are two different sets. Now how many variables you have for the rows and the columns is purely up to you. So you can have n number of variables for the rows and n number of variables for the columns. And like you would guess, you'd like to have it an odd number and not an even number, because probably an odd number wouldn't give you a middle value to maintain the system within. So yeah. And usually within fuzzy logic, it's very common to see 3, 5, or 7 variables at the max being used. But more than that, you're really not getting the entire effect of fuzzy logic, so as to say. If you're using to less, it doesn't make any sense. But if you're using 9 or 18 or something like that, 21, you're not exactly getting exact out of fuzzy logic. Okay.
Thank you very much, Shalom.
Yeah, thank you.
It was really good. You've passed. We're willing to give you your degree.
Yeah.